A and B can be anything. Now I want you to recall how we define functions. Again, the definition on the screen is the generalization it's the generalization of functions we have been learning. Okay. You imagine the map is a machine, a rule. You imagine the rule is a machine. Okay. To define the map, you specify three things. One thing is where the inputs are taken. The inputs is taken from the domain. Okay, the domain. We call A is the domain. So very shortly, so we're going to say that. So you're going to see that. Okay. And also, B is called the codomain. A map can process input and produce output. Right. The input is taken from the domain, and the output goes into B. And by the way, B is called the codomain. I said codomain. Codomain in general is not the same as the range. It's the set consisting of all possible outputs. I want to repeat, a codomain is the set consisting of all possible outputs. Okay. It may not be the same as the range. The range is the set consisting of only all outputs, right? Again, you imagine this F is a machine. A machine can process input and produce output. And the inputs are taken from the domain. The outputs are in the codomain. Okay. The requirement is that for every input, there's one and only one output. So that's what is the meaning of unique. I want to repeat. Okay. The only condition is that every input has one and only one output. So that's what we mean by unique. Okay. The notation of the maps for this course, again, I want to repeat, to specify a map, we need three things: the domain, the codomain, okay, and the rule, or how the machine works. We use A to denote the domain. We use B to denote the codomain. Okay. This part will give you how the function is defined. I mean how the map is defined. Okay. So what the rule is. I want to repeat, to specify a function, we use the following notation. Okay. Specify the domain, the codomain, and the rule. We're going to use a particular question to illustrate the meaning. Okay. For the people who came in late, get handout number 8 and unit 5. Okay. We'll work on the questions in part 1 by one. You look at the question. In the question, I want you to represent each of the following maps by specifying the domain, the codomain, and the rule. Okay, and the machine, how the function is defined, how the map is defined. I mean, okay. You look at question 1. We'll do one question at a time. You know, in calculus, the concept of function are so important in calculus, right? Functions are objects studied in calculus. In this course, the maps, in particular the linear maps, are used to study the relations between the vector spaces. Anyway, we'll do some questions first. Okay. In the process, you will see the meaning of functions. When you say F is a map from R to R, we have seen the meaning of R, right? R is the set consisting of all the real numbers. R is the set consisting of all the real numbers. When you say F is a map from R to R, the first R is the domain, okay? The second R is the codomain. And the rule is given by that. For every input in the domain, the output is given by the input squared. You take the square of the input, you have the output. It's essentially the same as the function we learned in calculus. Okay, the function was denoted by something like this. That was the function, right? But in this course, we are using a standard notation for the maps. Okay. So just the representation. Okay. The the map is denoted using f. To specify f, we have to specify the domain, so which is the first R, right? It's the set consisting of all possible inputs, all inputs. I mean, the domain is the set consisting of all inputs. Okay, you use a notation like this to indicate the map is from. Sorry, it's R, so not R2. I was too eager to jump to R2. Okay, and the map is from R to R. Okay, the first R is the domain of the map. The second R is the codomain of the map. Now we need to specify the rule or how the map is defined. Okay, you could write the thing in 2 lines or 1 line. If you want to write in 2 lines, I think we have plenty of space. I'm going to write in 2 lines. Okay, and the rule is given by the following: for each input, so now let's say x, the map can process the input to get output, right? The corresponding output is you take the number squared, you have the output. Okay, now let's use the map to recall some definitions or some terms. Okay, we mentioned terms like the domain, the codomain, the rule, right? Okay, for this one, so we're done the question. I'm just reviewing the terms. Okay, anybody want to tell me the domain of the function? The domain of the map, I mean. In this case, f can be anything. It may not be necessarily a function. Okay, the domain is R, right? The domain is the set consisting of all the numbers, all the real numbers, I mean. Okay, and the codomain is the set. Is that R? You look at the mouse cursor. Is that R? The R on the right hand side is the set consisting of all possible outputs. I want to, sorry, so yeah, probably I said something wrong. It's the set containing, the wording should be containing. The codomain, by definition, is the set containing all possible outputs. In this case, the codomain is the R on the right hand side. It's also R. In general, you can identify the domain and the codomain from the question. So because in the question we specified f is a map from R to R, right? The first R is the domain, the second R is the codomain. Okay, and the rule is specified by that. Okay, if you want me to read the meaning, every number in the domain is mapped to the number squared. So how about, to understand that, I'm going to give you some domain and codomain. I will give you some inputs. You tell me output. Okay. If I give you the input value of 1, so do you want to tell me the output? I did that in calculus actually. If I give you the input of 1, anybody want to tell me the output? For every input, you square the input, you have the output. So the machine is something like takes the square of the input. Okay. So please, so anybody? You are not warming up yet. So this one is so simple, right? The output is also 1. It's also 1, of course. You take 1 squared, you also have 1. Okay. Now let's try some other numbers. If I give you the input of 0, the corresponding output. So what's the output for the input of 0, please?
0.
0 squared is 0. Okay. If I give you the input of -1, so what's the output? You take -1, the whole thing squared. Okay. You compute -1, the whole thing squared. I will write it here. I said whole thing squared. It means -1 in brackets. You take squared. For the people who are not in calculus, so So there's a difference between these two things. So -1 squared is -1. It means -1. You take the square, so that way. If you compute that, it means -1 the whole thing squared, so which is 1. I think all of you guys know that. Okay, for the input of -1, the corresponding output should be 1, right? So can I just write 1 in here? So because for every input you take the square of the input, you have the output. Okay. One more? So maybe one more, okay. If I give you the input of -4, the output is 16. Use proper notations also, okay. It means we can also say -4 is mapped to 16. Okay. So be careful the notations. You have two types of the arrows. Okay. If you say the map is from R to R, you use that arrow. For the rule, for the machine, you use that type of the arrow. I don't know how to describe that, but I think you can see the difference. Right. At this point, I also want to mention the other terms, so which is going to be used later. The range. Also, I'm trying to tell you the range is different from the codomain. In general, the range is a subset of the codomain. Okay. How about I will give you the definition here. Okay. For a given map, I will write a full sentence. Okay. So maybe the definition. For a given map, I will use the general notation. So now let's say for a given map F from A to B, the range of F is defined. So can I just say defined as the set. The range, the set is defined as the set consisting of all possible outputs. I will just use the term inputs and outputs to define that, all possible outputs. The range is consistent. The definition is consistent as with what we learned in calculus. So anybody want to tell me the range? So maybe tell me the range in words. Give me a description of the range. It's because not all of you guys know the interval notations. The range is the set consisting of all 0 in the range. 0 is an output of 0, right? Again, the range is the set consisting of all possible outputs. Okay. Remember, under the map, so 1 goes to 1, so -1 goes to 1, so -4 goes to 16. Okay, and so on. The set consisting of all the outputs. I mean, the set consisting of all such numbers. Any number which is an output. Okay, is in the range. The range is the set consisting of all such numbers. Okay. We can use a inequality to denote the range, but I want to represent that in terms of a set. The range. So does that make sense? The range consists of all non-negative numbers. 0 is in the range, right? And you take the square of any number, it cannot be negative. Okay. Again, the range is the set consisting of all non-negative numbers. I said non-negative numbers. Using a inequality, you denote the set consists of all non-negative numbers using a inequality like that, right? It means the range consists of the set consisting of all the numbers greater than or equal to 0, right? But to specify it's a set, I want to use a notation like this. To denote the range. You listen to me carefully. I will read it, okay? The range is the set consisting of all the real numbers such that the numbers are greater than or equal to 0. It means the set consisting of all non-negative numbers. Okay. In particular, any negative number is not in the range, but any negative number is in the codomain. So do you see the difference between codomain and the range now? Again, in general, the range of a map is a subset of the codomain. May or may not be a proper subset. Okay. That's probably so enough comments on question 1. When we did question 1, we introduced many terms, many names. So you need to know the meaning. Okay. Now we move on to question 2. Okay. Of course, the main theme of this course is are the vector spaces. We study the vector spaces R2, R3, or the subspaces of R2 and R3 and so on, right? So in most cases, we concentrate on the maps so between the vector spaces. We work on question 2. Okay. Actually, the maps we are mostly concerning are linear maps, so you are going to see the meaning very shortly. Actually, later on, you are going to see the map G defined in question 2 is not linear. Okay. You are going to see why very shortly. But that's a map from R2 to something, from the vector space of R2 to something. Okay. This time the domain is R2. The set consisting of all the vectors with 2 components. Okay. And to R, this R is the set consisting of all the real numbers. So by that we mean all the inputs are taken from R2. Very shortly, we'll talk about the rule, okay, the machine, how the function, how the map is defined. Okay, so we have been so used to talk about functions. Give me a little moment to get used to the term of map, okay? Because I'm teaching 2 other calculus course. Okay, the answer is simple. Okay, G is the notation for the map, maybe the solution. G is the notation for the map. R2 is the domain. Okay, specify the domain. The G is from R2 to R2. Sorry, G is from R2 to R. This R is the codomain. This R is the codomain. This R is the set containing all possible outputs. Okay. This time the answer, I will write the answer in 1 line. Okay. The rule is here. Okay. Every input has 2 components. The input are the numbers taken from the domain, right? Every member in R2 has 2 components, right? So the input is a member for any member in the domain. It has two components. Okay. Every member in R2 is mapped to the notation is the following. Okay. You say every vector in R2, every vector in the domain is mapped to, or goes to. You can just say goes to the product of the 2 components. You see, it's mapped to xy, right? The product of the two components. You do need to check the product of the two components is in the codomain. You multiply two numbers, it's a real number. It's in the set of all real numbers, of course, right? So that's the answer to question G. Okay. To know the meaning, now let's try to get the output for some particular inputs. Okay. So we are done the solution. The following is designed to show you the meaning of the map. Okay. To know the meaning, again, the most important thing is to specify, to know how the map is defined. Okay. By that we mean, if I give you an input, how can you get the output? Okay. So now let's say if I give you the input of, so now let's say 1, 2. So anybody want to tell me the output? 1, 2 goes to the map as a machine. After being processed by the machine, the input 1, 2 goes to what? Goes to the product of the two components. Goes to 1 times 2. So that makes sense? So the output is 1 times 2 is 2. You multiply the two components, you have the output. Okay. I do want you to check the input is in the domain, the output is in the codomain. Okay. Can I ask you one other question? If I give you the input of, so now let's say 5, what is the output under G? What is the output under G? If I give you the input of 5, what is the output under G, under the map G? You don't know how to answer it, right? I was trying to trick you. 5 is not qualified as input. Again, 5 is not qualified as an input. Every input has to be in the domain. The domain is the set consisting of all the vectors with two components. So 5 is not an input, right? 5 is not qualified as an input, I mean. Okay. Now let's try one more, okay? So try another. If I give you the input of 0, 0, so 0 vector in R2, so that's qualified, right? For every qualified input, under the map, there must be a one and only one output. The one and only one output is computed by multiplying the two components. So it's 0 times 0. So of course it's 0, right? Again, the output must be a number in the codomain. For this one, I believe the range is the set consisting of all the real numbers. Now let's recall some terms. Okay. In this particular case, the domain is R2, and the codomain is also R2. Okay. Codomain is the set consisting of all the real numbers. The domain is the set consisting of all the vectors with two components, right? And the range. So anybody want to guess the range? The range is the set consisting of all possible outputs. Okay. I believe the range is also R. So any real number is in the range. In this particular case, the range is the same as the codomain. In general, the codomain is bigger. Okay. But of course, it's possible for the range to be the same as the codomain. Feel better? Again, so below this is not part of the solution. Okay, I was trying to use some questions to help you understand the meaning of the terms. Okay, now let's work on question 3. The maps we care the most are the maps, so like the maps in question 3. This map is linear, so very shortly I'm going to define what what is a linear map. Okay, but now let's work on question 3 first. The notation for the map is H. Okay, and the domain is R2, of course. You look at the mouse cursor. The notation is H. The domain is that R2. The codomain is that R2. Okay, and under the map, the rule, the definition of the map, the rule is that every vector in domain is mapped to the vector of that in the codomain. So basically, in words, you double the components, you get the map in the codomain, right? I mean, you get the output for the input of xy. Okay, now the answer to the question is easy. Okay, so maybe the solution. The notation of the map is H, and specify the domain, so which is R2. Specify the codomain, so which is R2, right? And the rule, the machine, the rule, the definition, all the same thing. I was trying to say the same thing in 3 ways. Okay. The definition is that every map in the domain every input in the domain, every vector in R2 is mapped to a vector in that R2. Okay. You just double the components, you'll have the output. I want to repeat, the definition is that for each input in R2, you double the components, you double the 2 components, you have the output. Okay. You can see the definition is that each input has one and only one output. Okay. So by that we mean each input cannot have more than one output. Okay. Each input cannot have more than one output. So that's what I'm trying to say. Okay. So we're done the question. Okay, still I want to give you some inputs and we try to get the output. Okay. Now for example, so this time I'm going to use different notations to represent the output for the input. I will give you 2 ways so that you can contrast. So now let's say if I give you the input of 1, 2, the output under the linear map, it would be 2, 4, right? It's 2, 4. In this case, again, I want to repeat the meaning. Under the map H, the output for the input of 1, 2 is 2, 4. I mean the output for the input of 1, 2 is 2, 4. To indicate that, we can also use the function notation we have seen before in calculus. I mean, the following notation is going to be comparable to the notation in calculus. We can also use a notation like this to denote the same thing. Okay. For the input of 1, 2, the output under the map H is denoted using, you can also say H of 1, 2. Can I just say H of 1, 2? How about we use some brackets? So this time you write equals instead of the arrow, an arrow like that. Okay. So the output of 1, 2 for the output for the input of 1, 2 is denoted using that. It equals 2, 4. So that makes sense. It equals 2, 4. It's comparable to now let's recall for the question we did in question 1. It's comparable to the output for the input of -1 is equal to -1 the whole thing squared, so which is 1, right? I want to repeat. you look at the mouse cursor. The whole notation here is for the output under H for the input of 1, 2. You can just say H of 1, 2. Okay. So that makes sense? Now we have two notations to denote the output, right? One notation is something like this. You indicate 2, 4 is the output for the input of 1, 2. You can also use H to denote that. Okay, H of 1, 2, the whole notation is the output for the input of 1, 2. So that makes sense? So later on for different linear maps, we're going to talk about the geometric meaning. But anybody can guess the geometric meaning of this map? To identify that, so maybe you try to identify the outputs for some input. Okay, so now let's say if the input is now let's say 1, 0, then the output is 2, 0, right? You double the components, you have the output. By that we mean if the input is here, if the input is can I use some notations? If I use U for the input to denote the input, I mean, okay. If the input is U, and then the output, so the output under H can be denoted using H of U, right? H of U, and then the output H of U. So do you see it's 2, 0? 2, 0 is here if we draw all the position vectors. Okay. And then likewise, if the input is 1, 2, if the input is 1, 2, 1, 2 is the vector with the first component of 1 and the second component of 2. I believe so 1, 2 is here. So now let's say 1 is here. So 2 is here. Okay. Thus can I use V to denote 1, 2? V is the vector, so now let's say 1, 2. Okay. Under the map H, the output for the input of 1, 2 is 2, 4. I believe 2, 4 is somewhere in here. So do you see the 2, 4? I do not want to write 2, 4. Instead, I want to write the output for the input of V. Okay. I wanted to remove that, but it's hard. Okay, now I will give you the description or the geometric meaning of H. Okay, so that makes sense. H doubles every input. I'm trying to say to get the output for any input, all you need is to double the length of the input. So do you see that? And then the output is in the same direction. I'm trying to say without the components, if I give you the input, so now let's say W is here. Geometrically, we have seen the meaning, right? You double the length of the input, and then you have the output. You double the length, and then you have the output H of W for the input of W. So did I make it clear? Later on for the questions, if I'm asking you for the geometric meaning, you just say H doubles the length of the vectors. Okay. You're going to see later on many linear maps will have the geometric meaning. It's actually quite interesting. Okay. So we're done question 3. So any questions so far? If you don't, we move on to question 4. Actually, it can be proved. So now let's talk about the question first. Okay. We call the map in question 4 the linear map associated with a matrix. I'm trying to say a matrix can determine a linear map. At this point, you remember a matrix can determine a map. Okay. You see A is a 2 by 2 matrix. Okay. Remember the following for now. Okay. A 2 by 2 matrix can determine a linear map. I haven't told you the meaning of linear yet. So now I'll try again. Okay. Now listen to me. Okay. A 2 by 2 matrix determines a map from R2 to R2. Okay. I will tell you. I told you the domain, the codomain, right? I will tell you how to specify the output for the inputs. Okay. I'm trying to say how to give the machine. Okay, now the solution. It's kind of the standard way. Now the solution. Actually, the output is given in here. It's given in here. For each input, the output is given in here. But I'm going to use the map notation to show you the meaning. Okay. The linear map for determined by the matrix A. So listen to me carefully. Okay. The map determined by the matrix A is denoted using T sub A. T sub A. This A is for the matrix. This notation is the notation for the map determined by the 2 by 2 matrix. Okay. A. You remember a 2 by 2 matrix determines a map from R2 to R2. The domain is R2, right? And then the codomain is also R2. The important thing is the rule, how the map is defined. So what is the machine? By that we mean for each input. We're going to specify the output for every input. Okay. For each input, so now let's say xy. For each input xy, the output is computed using the following in terms of the matrix. In terms of the matrix, the output for the input of xy is given by A, the matrix A times the input. Okay. Okay. Now we'll figure out the right hand side. The main thing is to get the right hand side, right? To get the right hand side, we do the following. We have to compute A times xy. A times xy. You treat the two things as two matrices. A times xy is equal to, in this particular case, A is the 2 by 2 matrix, 2 0 0 2, right? I'm trying to compute the right hand side. And then xy is a 2 by 1 matrix, the matrix with 2 rows and 1 column. It's nothing but xy. You multiply the two things as two matrices. So anybody want to tell me the two components in the answer? So your scratch paper is here. Anybody want to tell me the two components in the answer? It's defined. So because the A is a 2 by 2 matrix, right? And we treat xy as a matrix with 2 rows and one column. So xy is a 2 by 1 matrix. So that makes sense. And it's defined. It's possible to get the product of the two matrices. So anybody want to tell me the two components in the product? Two components in the product, please. Two components. Two components in the product, please. The first component is 2x, so that makes sense. It's 2x, and then the second component, 2y. 2x, 2y. Okay, so we have two components. If you want me to recall, the first component is computed using that row, the first row times that column, right? The second component is computed using that row times that column. Okay. Okay. So this means that each vector x, y is mapped to a vector in R2 in terms of two components as 2x and then times 2y. So do you see the two maps in question 3 and question 2 and question 4? I mean the two maps in question 3 and question 4 are the same. Okay. Actually, it's going to be true in general. Okay. Every linear map is associated with the matrix. Okay. By that we mean every linear map. So later on, so you are going to see is determined by a matrix. All right. So any questions? Any questions? So later on, so we're going to do more questions like that. But at this point, we're done part 1. I'm going to use at least one question to show what we mean by a map is linear. Okay. I will show you the definition first. Okay, you look at the definition on the screen. To say a map is linear, so there are two conditions we have to verify. Okay, I will show you the meaning of the two conditions. So when we do the questions. Okay, but the name of the two conditions. The first condition, we say the first two conditions. T reserves vector addition. The second condition is that T reserves scalar multiplication. I will copy the definition, okay, to PowerPoint so that I can make some more comments. The first condition, again, it's a map so with two conditions. The first condition, we say T preserves. T preserves so vector addition. The second condition is that T preserves scalar multiplication. Again, I'm going to use a particular question to show you the meaning of the two conditions. At this point, I want you to know the meaning of the two sides of the equation are different. Okay. For the left-hand side, you compute the sum of the two vectors, and then you apply the map. You get the output for the sum of the two vectors. Can I say that way? For the right-hand side, you compute the outputs of the two vectors, and then you add the two vectors. You see the meaning is different. For the particular map, I'm going to show you the meaning using a particular question. Okay. So did I copy this to the PowerPoint already? No, it's not that. Sorry. I was trying to copy that. If I want you to show something, you have to write proof. So I think we have seen that many times, right? Proof. To prove that, we have to choose two arbitrary vectors from the domain. Okay. So by that we mean we choose two arbitrary vectors from the domain. So now let's say for each vector, so now let's say xy in R2, we have to choose two. Okay, in order to show T preserves the vector addition, we choose two vectors. The first one, I use xy to denote the first vector. I think the second one I could use AB, right, for each other vector. So now let's say AB, so with two components. I said other, it may not be too precise. It's possible for the two vectors to be the same. Anyway, you choose two vectors from R2. We're going to show T preserves the vector addition. Okay. You look at the two conditions. I mean, well, we want to show, so condition 1 is true. Okay. For condition 1, we compute two sides of the equation, and then we want to show the two sides are equal. So do we want to use U and V to denote the two vectors? Okay, it doesn't matter now. Okay, it doesn't matter. We have, for the left hand side, we add the two vectors. We add the two vectors. So now let's say we add xy and AB, and then we apply the map T. Now I want you to compare that with the left hand side in the definition. You add the two vectors and then you apply T, right? Okay, so by that we mean you apply T to the vector. So now let's say you add the two vectors, you have x plus a. Okay, the second component is y plus b, I believe. Okay. Anybody want to tell me the output for the input of that vector? At this point, probably you want to give the description of the map. The description is that for each input xy, you double the first component, and then you get the negation, you get the negative of the second component. You have the output. So maybe you want to tell me the output, the first component in the output. The first component in output, please. The first component in output. You double the first component. I believe you have 2x and then plus 2a, right? I want to repeat. To get the output of any input, you double the first component and then you get the negation of the second component. You have the output. So the first component is 2x and plus 2a. You double the first component. You double the first component in here, right? And then the second component you get is negative y minus b. You negative the second component, you have the second component in output. Okay, so that's the left hand side. You see the left hand side is here. And then the meaning of the right hand side is different. For the right hand side, we have to compute the output for the input of the first vector, xy, and then plus the output for the input of the second vector, so which is AB. So we want to compute that. Okay. So likewise, the output for the input of xy, you have I think you have 2x negative y, the two components, and then the second component, the output for the input of AB, the same thing. You double the first component, it's 2a, and then you get the negation of the second component, so which is negative b. And then you add the two vectors, you end up with the same thing, right? So the first component is 2x plus 2a. The second component is negative y minus b, right? You see the two sides of the equation are equal. So by that we mean now I can say the left hand side t of the right hand side is the output for the input of xy, and then plus the output for the input of AB. The equation is true for any two vectors in the domain. I want to repeat, the equation is true for any two inputs in the domain. By that we mean T preserves the vector equation. T preserves the vector addition. And then you say something like thus: T preserves vector addition. Okay, that's the first condition. We still have to verify the second condition. Now I move on to the second condition. Okay. Secondly, I will show you the second condition. Okay. To verify that, you compute two sides of the equation. You compute t of a number times any vector u, and then for the right hand side you compute any number times tu. Okay. By that we mean we choose an arbitrary number for any number. We choose an arbitrary number c, and we choose an arbitrary vector in S. I mean, we choose an arbitrary vector in R2. Okay. We compute two sides of the equation. The left hand side, I believe we're trying to compute is t times c cxy. xy is v, so in the formula. Okay. To compute this, you perform scalar multiplication first. Okay. So by that we mean you get the output for the input of the scalar multiple, which is cx and then cy. Okay. Using the definition of t, the first component is doubled in the output. I mean, okay. The second component is the negation of the second component. I mean, the left hand side is the first component is 2cx, and then the second component is negative cy, right? That is the left hand side. For the right hand side, we have to compute c times the output for the input of xy. Okay, now you look at that. The right hand side is the c times the output for the input of u. In this particular case, u is xy, right? I just did not use the notation u. Okay. You copy the c, and then you get the output for the input of xy. Again, you double the first component, and then you get the negation of the second component, so negative y, right? You end up with the same thing, I believe, right? Scalar multiplication, c times 2x minus y. The first component you have 2cx. The second component you have negative cy. Now see the two sides of the equation are the same. So we have the left hand side, so which is t c xy equals c times the output for the input of xy. After seeing that, then you'll say t reserves scalar multiplication. I mean t preserves. scalar multiplication. After seeing two conditions are both true, and then you're done. Okay. Combine the two conditions, you say T is linear. Okay. Therefore, the given map T is linear. Okay. Again, the linear maps are the main objects we study in these two chapters. We still have two chapters left. Okay. Any questions about this? Any questions about this? I'll take that as no. We skip question 2, so probably on Friday I will give you a question like the question in 2. Okay. But now we move on to question 3. In question 3, we talk about the maps associated with matrices. Okay, in general. Actually, I want to do okay. Now let's work on. So can I just copy everything to PowerPoint? I will copy everything to PowerPoint. Okay. And probably you want to write something down. Okay. You remember one thing. Okay. Can I just say fact? Write down one thing, please. Okay. Write down the fact. A m by n matrix. A m by n matrix determines. Now I can say linear. Okay. A linear map from Rn to Rm. Actually, part 3 is designed for that point. Okay. I will show the meaning using some questions. We'll concentrate on A first. Okay. For the matrix A is a matrix, a 2 by 2 matrix with four entries. So -1, 0, and 0, 1. Okay. For that matrix, try to answer my question, please. Okay. A 2 by 2 matrix A determines a linear map from R1 to R1. I'm trying to ask you for the domain and the codomain. In general, a m by n matrix determines a linear map from Rn to Rm. In particular, m value is 2, n value is 2. Okay. A 2 by 2 matrix determines a linear map from R2 to R2. Okay. Now in the question, we are trying to determine the matrix determined by A. Okay. Find the map so determined by A. Okay. The solution has the following. I'm going to use T sub A to denote the linear map determined by the matrix A. We also say the linear map associated with A. Okay. A is a 2 by 2 matrix, so it determines a linear map from R2 to R2. I will tell you the rule. Okay, I will tell you the rule. I think we have seen the rule. It's very similar to the rule in the question we did earlier. Okay. for every input xy in the domain, the output is specified by the following. It's given by the following. It's determined by the matrix A. The output is A times xy. The output is A times xy. Okay. And then on scratch paper, you say something like, so that is, you write a new line. Okay. Write a new line. For each input, in general, the definition is that, but we have to compute that to get the output for each input of xy. On scratch paper now, okay, we compute the output for the input of xy. So you compute A times xy. You treat the two things as two matrices. Okay. By that we mean you compute. So now let's say -1, 0, and then times xy. At this point, anybody want to tell me the output for the input of xy? AXY is the output for the input of xy. So anybody want to tell me that? So sorry, I think I wrote something wrong in here. I copied A wrong. A is the matrix, 2 by 2 matrix. You have -1, 0. The second row you have 0, 1, and then you use that matrix A to multiply the input of xy. So please, anybody want to tell me the output for the input of xy? So tell me two numbers. The output for the input of xy, please. Anybody want to tell me the two numbers? You multiply. Okay, yeah. The first number is x. The second component is y, right? The first number is -x. The second number is y. Again, all you need is to perform a multiplication of two matrices. Okay, you use that row to multiply that column. You have -1 times x, and then plus 0 and times y, right? And then the second number is computed using 0, 1 times xy. I believe you have y. Okay, I review that, so just in case you forgot how to multiply two matrices. Okay. So the output for the input of xy is negative x and then y. Okay. So we are done. Question A. Okay. We are done question A. We concentrate on question A first. In question A, we want to get the linear map associated with the given matrix A. Very shortly, I will go back to talk about the geometric meaning. Okay, so that's question A. So can I move on to question B? For question B, B is also a 2 by 2 matrix. So a 2 by 2 matrix determines a linear map from R2 to R2. Now I will concentrate on question B. Okay, let's copy this to here again. I mean, for all matrices, I'm going to concentrate on question A. I will tell you how to get the linear map first. And then B, C, and D are designed to illustrate the geometric meaning. Okay. Very shortly, I will show you the geometric meaning. But now I want to concentrate on getting the linear map associated with the matrix B. Okay. For the matrix B, so now let's say 1, 1, 0, 1. That's a 2 by 2 matrix, right? Again, in general, a 2 by 2 matrix determines a linear map from R2 to R2. Okay. For this one, I also use T sub B to denote the linear map associated with B, determined by B. The same thing. Okay. A 2 by 2 matrix determines a linear map from R2 to R2. From R2 to R2. Okay. And then the rule is given by the following. For each vector in R2, for each vector with two components, x, y, it's mapped to, remember the definition. If you are given B, the definition for the output the definition of the output for the input of xy under the linear map is determined by b times the input. We have seen that twice already. Okay. And then you write a new line. Okay, and then by that we mean every input of xy is mapped to the output. So this time, can anybody try to get me the output on scratch paper? Okay, on scratch paper, the output is computed using b times xy. So which is you copy b is 1 1 0 1, and then xy. So please now the first component please. First component. You multiply two matrices. The first component I believe is x plus y, right? X plus y. 1 1 times xy. The column, the row 1 1 times the column xy. You have x plus y. The second component is just y. Okay. So the linear map is something like this. The first component is x plus y. The second component is y. So later on, it's really crucial to know how to describe that. Okay. Now let's say to describe the output for the input of xy, the description is something like the first component is the sum of the first two components. Now let me try again. Okay, the first component in the output is the sum of the two components in the input, and then the second component is the same as the second component in the input. Okay. So later on, for other purposes, for many purposes, it's important to identify that. Okay. Okay. Now for this one, to make my point, now let me try to get some outputs for some input. If I give you the input of 1 2, so anybody want to tell me the two numbers for the output? The output for the input of 1 2. The output for the input of 1 2, please. You do not have to multiply two matrices. You just look at the final form. The first component. The first component in the output, you add the two components in the inputs. So the first component is 2. 2 is 1 plus 2. Okay. The second component is the same as the second component in the input, so it is 2. So do you have that? Does that make sense? That's the meaning of the linear map. Okay. So we're done question A for the matrix B. Okay. Again, I will go back to the geometric meaning if I have time. Okay. But now I want to move on to C. Now let's look at C. Now we look at C. In question C, you are given a 2 by 3 matrix. C has 2 rows and 3 columns, right? C has 2 rows and 3 columns. C has 2 rows and 3 columns. So m value is equal to 2, m value is equal to 2, and n value is equal to 3. So do you want to recall a m by n matrix determines a it's here, okay, the fact a m by n matrix determines a linear map from Rn to Rm. A 2 by 3 matrix determines a linear map from R3 to R2. I was trying to use m value of 2 and n value of 3. Now let's go back to this question. Okay, a 2 by 3 matrix C determines a linear map from Rn to Rm, from R3 to R2. Okay, so I still use T sub C to denote the linear map determined by C, or the linear map associated with C. Okay, a 2 by 3 matrix determines a linear map from R3 to R2, so don't be confused, okay? I will show you how T sub C is defined, the linear map. We have seen the domain, we have seen the codomain, right? And then now the definition, the rule, okay? The input has to be taken from R3. R3 consists of all the vectors with 3 components. So that makes sense if I use xy to denote the components in this R2 for the input. I'm trying to say every input has the form of x, y, z. Every input has 3 components. Okay. Maybe I want to rewrite that. Every input has 3 components, x, y, z. This thing represents any input. Okay. Now we are trying to compute the output for the input of x, y, z. In this case, the output is computed using C as a 2 by 3 matrix. The output is always computed using the given matrix. In this case, C. Okay. In this case, C times x by z times the input. Maybe for this one, I will make the wording a little better. Okay. So this argument is for the matrix C. For the matrix C, C is the C in the question. 1, 1, 0, 0, 1, 0. It's better. For that matrix C, we are trying to determine the linear map associated with C. Okay. The second line has the general definition. The third line, you have to give the rule for the special, for the particular matrix. Okay. By that we mean each input x, y, z is mapped to C times x, y, z. On scratch paper, you compute C times x, y, z, right? So C times x, y, z is computed using, you copy C, is computed using 1, 1, 0, 0, 1, 0, and then times x, y, z. So maybe just tell me the first component, please. So just tell me the first component. If you can get the first component, then you know what's going on. Tell me the first component, please. The first component for the input of, I'm looking for the first component of the output for the input of x, y, z under C, under the linear map T sub C. So please, the first component, use that row to multiply that column. Are you guys listening to me? So it's x plus y, okay. And then the second component is, what's the second component? Second component is just y, right? By that we mean you use the second row to multiply the column. You have y. I think you have y. Okay. Now we have T sub C. T sub C is the linear map associated with the matrix C, right? Okay, to understand that better, to understand what's going on better, I will get some outputs for some particular inputs. Okay, if I give you the input, so now let's say 1, 1, 1. Now let's just do y. Okay, under TC, under T sub C, we have the output for the input of 1, 1, 1. The output has to be a vector in R2. The output has 2 components. The first component is computed by adding the first 2 components in the input, so which is 2, right? 1 plus 1 is 2. You add x plus y. I mean, x plus y is 2, right? X value is 1, y value is 1. And then the second component is the same as the second component in the input, so which is 1. I think what I have been talking about sounds simple, but it's going to be useful very useful later to do many other questions. Okay. For the matrix M, I'm going to squeeze the solution in here. I think I have enough space. For the matrix M, we only answer question A. Okay. For the matrix M, M is the matrix with a 3 by 2 matrix with 3 rows, 2 columns. Okay. I mean, M has 3 rows and 2 columns, 3 by 2 matrix. The first row 1, 2, the second row 3, 4, the third row 5, 6, right? For this question, I'm going to label the size. You do not have to, okay? It's a 3 by 2 matrix, 3 rows and 2 columns. So T sub M. Okay, so please, so tell me the domain. Is the domain R2 or R3? A 3 by 2 matrix determines a linear map from R1 to R1. So just tell me the domain, please. If you can tell me the domain, you know what's going on. In general, a M by N matrix determines a linear map from Rn to Rm. In particular, a 3 by 2 matrix determines a linear map from R1 to R1. Come on. It's easy. A 2 by 3 matrix determines a linear map from R2 to R3. R3, okay. I want to repeat. A 3 by 2 matrix determines a linear map from R2 to R3. You kind of reverse the order. A 3 by 2 matrix determines a linear map from R2 to R3. You reverse the order, okay? I mean, you reverse the order of the size of the matrix, and then you get the domain and the codomain. Okay, now let's see what's going on. Okay, so by that we mean each the input has to be a vector in R2, has 2 components, right? For each input, we are trying to get the output under the rule. The output is computed using the matrix times the vector. The matrix times the input. The matrix is 1, 2, 3, 4, 5, 6, and then the input is x, y. So in this particular case, okay. Okay. And then on scratch paper, you have to compute the right hand side. By that we mean on scratch paper in here. Okay. You have to compute m times xy. By that we mean you compute m times xy. If you get the domain and the codomain right, the multiplication is always defined. This one has to be a vector in R3. I mean, have 3 components. The first component, okay, is x plus 2y. The second component is 3x plus 4y. Okay. The last component is 5x and then plus 6y. It means each vector in R2 with 2 components, xy, is mapped to a vector in R3 as a vector in R3 has 3 components. The first component, x plus 2y, you just copy from the scratch paper. The second component, 3x plus 4y. The third component, 5x plus 6y. Okay. That's the answer to question 8 for the matrix M. Okay. Okay, now let's try to get some input. Okay, try to get some outputs for some given inputs. Okay. I'm trying to say how to understand the meaning of the map. Now let's say if the input is 1, 2, I'm trying to get you the output for the input of 1, 2. Okay. In this case, x value is 1, b value is 2. I mean x value is 1, y value is 2. Okay. And then the first component is x plus 2y. I believe you have 5. X plus 2y is 5. The second component is 3x plus 4y. Do you have 11? The third component is 5x plus 6y. Can I do that mentally? Is that 17? I think 17. Okay. I'm trying to say that is the linear map associated with the matrix M. Any questions about this? In next class, for some other topics, I will talk about the geometric meaning. So don't worry too much about B, C, and D. Okay. So these are the questions designed to illustrate the geometric meaning.